Bismillahirrahmanirrahim. Assalamu alaikum, everyone. Welcome to this course on data structures and algorithms. Because this is our first interaction session, so I plan to spend some starting time on introduction, and then we'll get to the contents and organization of the course. So as far as the introduction is concerned, let's start with my introduction. So my name is Malik Jahan. I am an associate professor at Lahore University of Management Sciences in Pakistan. I have been teaching data structures course for more than 10 years now. And my recent offering over here was last spring. So it's really a matter of pleasure and honor to interact with all of you and teach this course to your batch. My primary, I usually teach at undergrad level, but like my area of research is related to applied machine learning. And I do different research projects where machine learning can be applied in the fields related to agriculture, livestock, and water management. Uh, so as far as LUMS is concerned, so LUMS stands for Lahore University of Management Sciences. This is one of the top universities in computer science in the region. So according to CS rankings, LUMS is the #1 computer science university in Pakistan, and it is #6 university in Asia in computer science, and more specifically in computer systems. Though it's a volunteer stuff, but I would really like that if you can briefly introduce your background and the kind of expectations or maybe some suggestions you might have for this course so that we can optimize this experience. We can make it as good as possible. So we can start from any of you because actually we have more than 60 students enrolled in this class. So, but we know that due to the unfortunate circumstances, so many people might not be able to join the live sessions. So we'll keep on recording all sessions, and the recordings will be uploaded over YouTube. I'll keep on sharing the links through this Gaza Moodle. Would any of you would like to introduce yourself briefly?
Can I start?
Yeah, please. Yes.
Okay. First, I'll introduce myself. I'm Lajain Al-Wahidi, and I'm, as you know, a student from Gaza Strip. But now I'm abroad Gaza. I'm in Egypt, and as you see, I'm trying to continue my learning here in Egypt, even if my parents are still there in Gaza.
I see.
The first thing I would like to add is that it's an honor to us also to have an instructor like you. So this is the first time to have a foreign instructor, and I'd like that it's from Pakistan.
Thank you so much.
Uh, Thank you.
Yeah, go
And
ahead.
I would like to ask that I saw in the model that the study will be with the programming language C++. Um, I haven't studied this language, and I did see that there's a problem in studying it, but I think that maybe most of us will find it more easy if we studied like Java, because I think Gaza Strip universities teach Java, like the Islamic University, UCAS, which is my college. So I don't know. Maybe you can make um, research. I don't. I forgot the use the word.
Yeah, that's perfectly fine. Yeah, that is a very good suggestion, and thank you for your introduction. It's very nice to know you. Uh, and so okay, so that's a very good suggestion which you have shared, that you might not be very comfortable with C++ and you would prefer Java. So let's see what others suggest. So because in this course we'll have to like stick ourselves to one language, but I'm flexible, right? We can switch to
Yes, yes,
Java.
but
So
yeah, but I would
Mhm.
like to add that there is no problem if it was C++. I like to study things by myself. I have no problem. But
Oh, I
it was
see.
just a suggestion. Yeah.
Okay.
Thank you.
Yeah, thank you very much. And like, okay, so I take your point. Like on top of that, I would like to add and share with all others that personally I would like to teach using C++, not due to the reason that I'm comfortable with. I can teach both in, I can actually teach in Python, Java, or C++. But the reason is that C++ is treated globally, is treated as a mother language of all languages. So if you become expert in C++,
Okay.
it becomes very easy to transition to other languages. But like I'll go
Okay.
with
No
the
problem.
majority of the opinions, right? So whatever like you people will suggest.
Okay. Okay.
Yeah.
No problem.
Thank you. Thank you. Okay. Who is the next volunteer? So the people who have just joined, we are introducing ourselves to each other. Yeah, Ayat, please start.
Hello, my name is Ayat Nassar. I am studying computer system engineering. Actually, I agreed with Lujain about studying in Java.
Mm-hmm.
It's better because the most of students did take this course and know about Java more than C++.
Okay. Okay. All right. Thank you very much. Okay. Next volunteer. Who else would like to introduce him or herself? Firas, would you like to introduce yourself? Or maybe Hiba, Mahmood, Bara, or Asil. This is a completely volunteer activity. If any of you would like to introduce yourself. Okay, that's fine, right? So it's quite possible that you might not be able to listen to me, or you might be like feeling any difficulty in this whole thing. So we can introduce. Okay, I think Hiba has unmuted herself, perhaps. No. Okay. Uh, so let's now get to the data structures part. So we are like almost okay with our introductions. And so let's try to understand that what is the data structure? What do we mean? So I don't have like a lot of assumptions or prerequisites, that I'm not expecting that you are already familiar with data structures, but some of you might have done similar kind of stuff in your previous programming courses, which should help us in building up this course. So let's start with a very fundamental concept, that what is data? Because when we say data structures, we're talking about two components. One is data, other one is structure. So data comes in different formats. Data could be numbers, could be text, could be images, could be videos, or could be any mix of all those things. So anything which makes some sense in the real world to us as humans, we call it data, and we try to process it. So when we say structure, so structure is essentially the container. So data is content and structure is the container. So when we say what is a data structure, so data structures are primarily data containers. And there are a wide variety of data containers. Their variety primarily depends on the need, depends on the kind of use case we have at hand. or the kind of stuff we want to get done using that particular data structure. So where does the data come from? Data might be coming from a wide variety of sources. So for example, our business and economic activities generate a lot of data. So whenever like we do any transaction, we are generating a data point. Our news, social media, tweets, comments on Facebook, on YouTube, on Twitter. So all those things are data sources, and each activity is creating a data point. Even in the today's era, if we just make a click on while doing some browsing, so that is creating a data point. So we have so many other sources of data like sensors. We have Internet of Things, which means that we have a pool or network of sensors. We have wearable devices which keep on monitoring our movements, our activities, our health, our physical activities, our geographical locations. For sensors, we have temperature sensors, we have humidity sensors, sensors for fire detection and those things. So all those things are feeding data. They are creating data. And then all these different sources come for a reason. And most of the time, the reason is a real world application. So for example, we use data in healthcare to diagnose diseases using intelligent algorithms or intelligent programs. We use data in education, like Coursera or online courses. We use it for digital marketing. And then there are so many other types where where the data may come from. So data types, the data comes in different forms. It might be text, might be numbers, might be images, audios, videos, or mix of all of them. So if you just look at this picture, what is this? Any guess? So Jen, yeah, go ahead.
Fox.
Excellent, right? This is a fox. What is this?
I don't
Okay.
I don't know the name in English.
Okay, so this is a bird, which has a very long beak, and in Pakistan in Urdu this is called hudhud, right? So I also
Yeah, we call it hadad in Arabic.
okay, good. Okay, so oh yeah, thank you, hudhud. Yeah, so the use case is that this is actually a like a hypothetical story that fox and hudud actually live together. They become friends, and then fox is actually famous in our stories. Fox is famous for its cleverness. So fox asks the hudud to like do some party. So fox invites hudud and serves food in this flat vessel, the kind of plate which you can see on the screen. So the food is served, that's a like somewhat liquid kind of food which Fox has prepared that is served in this plate. And when hudud comes in, because hudud has very long beak, it tries to dip beak in that flat vessel, but you're like the food is spread all around. So Fox keeps on eating food from that plate very conveniently, but hudud has like a lot of difficulty in eating food from there. So at the end of day, hudud actually remains hungry, cannot fulfill its food need, but like all of the food is eaten up by the host, which was fox in that case. So hudud gets very angry on that, and then hudud thinks of a plan, and he invites the fox at his place and serves the food in a vessel like what we see on the screen on the right side, which is like a bottle, right? It's a it's a kind of deep flask. So the Hodot actually serves food, pours food into that thing, and that food is like filled in that column, in that vessel. So now when the guest, which is Fox in this case, comes in, she tries to eat food, but is unable to put her mouth inside the vessel because that's a narrow opening at the top of the vessel. But Hood, because of its long beak, is able to access that thing. Now the objective of sharing this example with you is that there are two end users. One is Fox, other one is Hudud. Same kind of food is being served in two different containers. So the ease of accessing the content, which is food in this case, is very, very different when we shift from one kind of container to another kind of container, right? So the content is same, food is same, but the ease, when we shift from one container to another one, it changes. Same kind of stuff happens in the case of data. If you pour data into a container, sometimes it becomes very easy to access the data. And if we pour the content or store the content or store the data into a difficult kind of container, then it becomes really difficult to access it. So why we study data structures? Like, there could be many reasons, but one important reason is the time consideration. We need to look at this angle, that in order to process that particular data, what will be the amount of time which will be required. Second consideration is what will be the amount of memory which will be required to store that data. What will be the amount of energy which will be required to process that data. So all these things might not be very important if data size is small, but might be very challenging if the data size is very large. So what we'll do is that what kind of data organization is the right choice in a given scenario? That's the kind of question which we'll address in this course. How to design a data container, how to design a data structure, that's what we'll learn in this course. How to analyze the performance of a data structure with respect to its associated operation. So by data structure, we mean the container of data. So if you are able to recall those two like physical containers for food, similarly, we might be having data containers in computers' memory to store data. So we need to analyze their performance in the context of different associated operation, that which of them is more convenient or efficient for us. So one like critical thing which we learn in this course is that how to analyze the performance of a data structure. And like then that once we have a like decent amount of knowledge or decent amount of theory at the back end, we need to understand that how to implement those data structures using our language. So based on the feedback which both of you have shared with me, Ayat and Lujan, will be opting for Java later on. But like in today's session, I actually mentioned C++, so just pardon me for that thing. So I'll go with your advice, and we'll move to Java. Okay, so it's a question which we need to ask ourselves, that why we need to study, why we need to understand, why we need to have a good grip over data structures. So data structures is an important cornerstone of computer science foundation. You may not be able to do any sensible activity in the computer science domain without decent control over data structures. So data structures related questions are very common in the top-notch industry around the globe. Right? So you think of multinationals, you think of these tech giants like Google, Microsoft, and Facebook, or you think of some local industry in any country. Like for a fresh graduate, it's very common that people ask questions related to data structures. So if we don't have a like decent control over data structures, we can't do much in the computer science domain. And then the question is that how to believe in this claim that this is really important. Like I would strongly urge you that try to explore, try to Google the top 10 or top 20 interview questions at Google, top 10 questions or interview questions at Facebook, and those kind of things. What do people expect from a CS graduate? So in most of the answers, you might be seeing data structures all around. And in this exercise, in our meetings, in this course in data structures, one of my objectives would be to prepare you pretty well so that you can address those kind of questions whenever you face the industry interviews. So the next term which we will be studying in this course is called abstract data type. We'll be using this term very frequently in the course. We also term it as ADT. So ADT is a conceptual data type that has well-defined behavior. For example, we might be having certain containers which we'll call stack. So stack is a kind of bucket which is closed on all three sides, on both sides, vertically and on the bottom. And then there's only top where we can pour content into the stack. So just think of a stack of books or stack of plates. They are placed on top of each other. So if we have to remove a plate from the stack, so the last plate we would have put there will be the first one which will go out. So that's the kind of behavior of that particular container. Or queue is another kind of thing. So for example, we make up queues like to get a particular service. So for example, we might be having queues in banks or in some other service providing office. We have seen queues quite commonly in our daily life. Priority queue is a queue where like certain items in the queue get more priority over the others. Uh, and like when we say conceptual data types, so if you, I'm sure you would have been like familiar with Facebook as a user, but like just imagine that how Facebook works at the back end, how it stores information about you, your friends, your pages, the kind of pages you liked, and so on, and your posts. So each friend is one thing, one type, one conceptual data type, one ADT on Facebook. One page on Facebook is one ADT. And then that ADT has a lot of features inside it, a lot of operations. So for example, one friend has its name, its ID, its password, its picture, and its posts. Plus, that friend can do certain things. It can like pages, it can add friends, it can delete friends, and so on. So all those are the associated operation of that data type. So the question is that how to implement an ADT. So implementing an ADT now demands us to recall our programming knowledge. So I'm sure because like we are now shifting to Java, so that thing should be we should be able to recall our classes. So you might have studied classes in Java because even if we have to write the smallest possible program in that public static main, we need to create a class. So, but if we create a class for our task, for our job, for our purpose, like we create a class for stack, for queue, for a friend on Facebook, so that class will serve eventually as an ADT. So within that class, what we know from our programming background is that we can create attributes and we can create different methods, which will represent behavior of that particular data type. So ADT is an abstract thing, right? Is a concept. But within that concept, we need to be very much clear mentally that what kind of stuff we are talking about. When we like implement that thing in terms of code, so that then ADT becomes the concrete implementation. So in Java, we'll be seeing the concrete implementation. And that concrete implementation is termed as data structure. So that's what we call data structure. So once we code an ADT, then it becomes a data structure, or theoretically we call it data structure. Now you can ignore things on this slide. I was planning to have some recap related to C++ stuff, but I'm skipping over that part. And from the next session, we'll focus more on Java part. And meanwhile, I'll also like make some changes on the kind of thing which I've uploaded over there on Moodle. So we'll be doing this Java programming, and Java by default is an object-oriented programming language. So we'll be using those fundamental concepts of object-oriented programming. We need to understand that how to define a class. We need to know another thing which you might have studied in your programming courses, which is composition, which means that one object can contain another object, or within one class, we create attributes which are actually objects of another class. So those are the kind of skills which we'll need over here from Java perspective. Recursion is very important for all programming and data structure related stuff. So when a function calls itself, that concept is known as recursion. So we'll do a quick revision of recursion most probably in the coming session. And you can skip pointers because Java does not have pointers. Instead, it has references, and everything is most of the time by default references. So now the course, the way course is going to be administered. I'm the only instructor at the moment, and that's always the plan. So I'll be executing this course on my own. And so there are two major grading components in this course. I tried to keep them very much viable and flexible for all of you so that you can conveniently do them. So there will be some programming assignments. So half of the course weightage will go in programming assignments. And then there will be a final exam towards the end of the semester. So this semester is going to span over 7 or 8 weeks. So which means that we'll be concluding our semester somewhere around first week of September. So half of the grading will go in final exam, or half of the weightage will go in final exam. So a little bit about programming assignments. So each assignment is going to be a strictly individual work. I would strongly suggest that you try to put individual effort so that your learning does not get compromised. So start working assignments on time. As you get time, as you see the assignment, please start working on them, and that will help us to release the stress. We won't feel pressurized in terms of time and deadlines if we start working on time. So expected number of assignments in this course are 5. So roughly, like I'm planning to have like equal weightage for each assignment. So one assignment is going to be of 10% weight. Okay, so this is the textbook which we'll be using in this course, but like you may ignore this C++ part. Actually, the good thing is that the same pool of authors, Goodrich, Tamasia, and Group, they have written a book for data structures and algorithms in Java. So we'll be using that book instead of this C++ book. Okay, yeah, that could be another like good suggestion from Lujain, that I can make a survey asking students what's the language that they have studied, C++ or Java, so that we can go for something common, right? So one thing which you might be able to understand even right now, that for this course we'll have to stick with one language, but like I'm open to all of those 3 languages which I know: Java, C++, and Python. And I'll go with what I would like you suggest. So by the time I actually share the next slide, I would strongly suggest that please join the WhatsApp group. So that should help us to have a smooth communication. So link of the group is there on Google, on this, Gaza Moodle, and you can find it in announcements. Please join that one so that we can conveniently communicate with each other. Okay, so what we've done so far is that we have tried to define what a data structure is. So essentially, it's a data container, and that container needs to be characterized by different attributes, by different properties. And each data container has to have some set of associated algorithms. So algorithms are the kind of operations which define behavior of the data container. So for example, if we have a stack, so how to insert elements in the stack, how to remove elements out of the stack. So those are the kind of operations which will define individual algorithms for their data structure. So algorithm technically means this is a recipe. This is a sequence of steps to perform a certain task, just like a recipe to cook food. So recipe is a sequence of steps which usually we follow, and I'm emphasizing over sequence. Sequence is very important. Just imagine a recipe. If you mess up the sequence, we might not be ending up into the desired product. So same happens with algorithms. So in order to design an algorithms, in order to code an algorithm for a particular data structure, we need to be careful about the sequence, and within that sequence of steps, we need to define the associated behavior, the kind of operation which that algorithm is supposed to perform. So how to, for example, insert an element, how to delete an element, or how to search an element. And then the important thing which we talked about a while ago is that how to analyze performance of each algorithm. Okay, now let's try to start with the simplest possible data structure. So in my views, simplest possible data structure is a single variable. Just imagine one simple integer variable, right? So when we in Java we write int x, So we create a data container, which is a small placeholder in the memory, which can contain only one data item. And that data container has a name, has some memory address, has an associated data type, and we can store one data item in that data container. So what kind of algorithms we can think of, what kind of operations we can think of, or what kind of behavior we can think of about that data structure could be many small things, like how to store an element, how to retrieve or fetch an element from that variable, how to update or change that particular variable, how to display it, how to share it with someone else. So all those are the associated algorithms. And now the question is that who will decide the algorithms? It's going to be you. It's going to be the designer of that data structure. So because before you start coding, you need to imagine, you need to visualize, you need to document the overall functionality, the kind of problem you are about to solve. And then you start coding that thing. And another thing, like administrative thing, which I didn't mention, I forgot to mention actually. So all these sessions are like, they are in a way, please don't treat them as the formal sessions. You are more than welcome to interrupt me at any time, right? So just like let me know if you want to say a comment, or like if you have a question or confusion at any point, just let me know, right? So that all of us, the objective is that all of us should try to stay on the same page as we go along in the course. Okay, the second level of or data structure which we can think of is that it's a sequence of different variables, which we call in programming, we call it array. So array is a placeholder for multiple data items. Uh, so so the kind of characteristics, unlike a variable, so one different characteristic is that it has different elements. So which size is one characteristic. How many elements can we possibly store in that array? Another important thing which you might be able to recall from your programming days is that all those memory locations in an array are contiguous. They are just next door neighbors to each other. In the memory, they create a street of placements. And if you know memory address of the first element, it's always easy to jump to the neighbor or neighboring element. And then all elements in an array have the same data type. So these are the kind of characteristics of that array, that data structure, which is the probably second simplest one. So before we talk about algorithms or operations of an array, one question could be that why do we need array, or in what kind of situations we need to use arrays? So because array is a sequence, a collection of elements, which that means that in order to create anything which looks like a list, we can store array. So if I have to store, for example, list of my students in data structures class, I might be creating an array which will just contain their IDs. Or if I contain an array of type string, I can store their names. Or if I create an array of type, let's say float, I can create their grade points. So, or marks. So once that kind of, so essentially array is being used to represent or build or implement something which looks like a list. List might be a list of events, or could be like, we can think of so many things in terms of a list. So associated operations could be that how to add an element in a list, how to remove an element, how to search an element. So for all the data structures which we'll be studying in our coming days, these three operations are treated as very fundamental and primitive operations. That means that, like given any arbitrary data structure, we need to know that how to store an element, how to put in a data object inside the data structure, how to delete an element from there, how to search an element from there. So all these things are like common, but the mechanisms will change, because if the container changes, we can always recall that analogy of Fox and Hudud, that if the container changes, so your convenience or ease of accessing that food or your item of your interest also changes. So you can't add or remove things with the same convenience if the underlying container is changing. Okay, so In this course, we'll be studying data structures, so we call classic data structures. Array is one of the classic and simplest data structures. And we'll be focusing on efficient procedures to solve large scale problems. So when we say large scale problems, that means that what does that mean, right? So if you if you try to explore history of computers, like we used to have very small very inefficient devices like maybe 2 decades ago. Our processing power was small, our memory space was small. So even in order to get a small task done, usually our computing devices used to take more time. So if we try to compare this history of computer hardware progress versus algorithms, uh, we'll be making a like quick comparison in a while. But before we do that thing, let's have a look at this problem, right? So it's a peak finding problem. The problem is described as follows. Given a set of numbers stored in one-dimensional array, find one of the peaks. For the sake of clarity, the second sentence says that we are not interested in the highest peak. Now, the question is that how to solve it, what kind of problem we are looking for. So any idea about the number of steps required for an array of 100,000 elements? If we have 100,000 elements, what do we need to do? So some arbitrary numbers have been given to us, and we are interested in finding the highest peak. Any guess about the number of steps required to find the highest peak? Could be any wild guess.
Can you repeat the question?
Yeah, so we've been given a set of numbers which are stored in one array, and our task is to find one of the peaks. So peak is like somewhat like this, right? So if you look at this kind of the diagram which is there, so our task is to find a peak. So how do we characterize a peak? So if you look at this whole signal, the blue one, so this looks like somewhat what we see in ECGs or those kind of signals. So each red dot is a peak. So the first question is that how to characterize, how to define a peak. So all these numbers, all these blue points are stored in one array.
I think the peak must before it and the after it must be less than.
Excellent, excellent. Yeah. So the numbers, the neighbors before and after should be smaller than that number, right? So then this will be the peak. And because our target is to find a peak, so we can start scanning the array. And as we
The
encounter
first element, yeah, the first element will be considered as the highest peak because it's the initial one.
yeah,
And then we'll start taking this number or this element and comparing it to the coming.
correct. Yeah. So, but like as we encounter a peak, so peak is a number whose previous and after or next element are smaller. So then that number is a peak, right? So in this like version of the problem, we are not interested in the highest peak. So we can conveniently like output that using that if statement. We run a loop from the start index till the last index. And as we encounter that kind of thing whose neighbors are smaller than that number, so we return that number. Uh, does that make sense?
For me, yes.
Mm-hmm. Yes. Ayat, you wanted to say something?
I wanted to say before Lujain that we can use a loop to find and compare each index by the index before it.
Before it and
And
after it as well, right?
yes,
Very good, very good. Completely correct. Okay. So I would strongly suggest, because some of you might have taken some time since you're like class programming exercise. So in this course, what I'll do is that I'll keep on introducing a lot of homeworks. Homeworks means that they are ungraded, so you don't need to submit back. So they're just for your practice, right? So the first homework in this session is that try to write a program to find a peak, right? So because it's ungraded, so language is your choice. So if you're comfortable with Java, just write it in Java, try to code it, and and then just keep it with you, right? So you don't need to submit it. Okay, now we are actually going to we are going to do an important exercise, and I would strongly suggest that please stay with me in these calculations so that I don't mess up anything over here. So n is a variable. That's the input size. We have been given 10 million numbers. And then there are two scenarios, which I'm going to show you. So our task is to compute exact physical time for both of those situations. By physical time, I mean the time in hours, seconds, minutes, or like the time which we see on watch. So there are two computers. One is computer A, other one is computer B. Both of the computers have been given the same input. So input size is 10 million numbers. And task is to sort those numbers, to arrange those numbers. But the difference is that for both of the computers we are employing two different sorting algorithms. So the computer A is using an algorithm which we call insertion sort. You don't need to worry about that, how does it work, but we have been given that algorithm. And we also know that how fast is that algorithm. So number of instructions to execute are 2 multiplied by n square. And if you look at computer B, so that uses another algorithm, and number of instructions are 50 multiplied by n multiplied by log of n. So that's the kind of characterization of those algorithms or programs. If you look at speed of computer A, that is 1 billion instructions per second. If you look at speed of computer B, that is 10 million instructions per second, which means that computer A is a super fast computer. So the kind of stuff which I wanted to do with you over here is that, so let me try to use some kind of annotation over here. So n is 10 million numbers. So 1 million contains how many zeros?
6.
Thank you. So n is equal to, so I'm just writing it as n contains 10 raised to power 6. So n is exactly 10 raised to power 6. And so that is the size of the input. So 1 billion contains how many zeros?
9.
9. Very good. So 10 to the power 9 is the time 10 to the power 9 instructions per second is the speed of computer A. So these many instructions per second is the speed of computer A. So now the total number of instructions which we need to execute over here are 2 multiplied by n multiplied by n, which means 2 raised power 2 multiplied by 10 raised power what? What will be n square?
7,
Uh,
right?
n is 10 raised power
Because
6.
it's 10 million, yeah, it's not 1 million. So
Sorry.
it must be,
Yeah,
I didn't,
shouldn't it be n 10 raised power?
10 power 7,
No, it's
right?
sorry. 2 times 10 raised power 6 times 10 raised power 6, because it's n square, right? Okay, is it right?
I didn't get.
Mm-hmm.
I didn't get why n equals 10 power 6. Isn't it 10 million? So it must be 10 power 7.
Absolutely correct. Thank you for thank you. So you are absolutely right. So because the n is actually not 10 to the power 6, n is 10 times. So 1 million is 10 to the power 6. So n is 10 to the power 7, right? You're right. Thank you for pointing it out. So n over here is actually 10 times 10 to the power 6. So both of them are going to be 10 to the power 7 and 10 to the power 7. And this will give us what? 2 raised power 2 multiplied by 10 raised power what?
14.
10 raised power 14. Thank you. So these are the total instructions which we need to execute on computer A. And computer A can execute 10 raised power 9 instructions per second. So the question is that if in 1 second these many instructions are being processed, so what will be the amount of time required to process these many instructions? So can you please like use your notes for a while if you have, or do some basic number crunching? So we are interested in the time which will be required for computer A. So what will be the amount of time in terms of seconds or minutes or something required over here? So that should be somewhat 2 times 10 raised power 14 times 10 raised power minus 9. Is it so? So this gives us 2 times 10 raised power 5. What? Seconds? So 2 raised power 5 means that I'm using, I have 5 zeros over here. So if I use this basic formulation in Excel, this gives me that 200,000 seconds. And that gives me, if I divide it over 60, so that gives me around 3,000 hours. And if I divide it, sorry, that gives me that many minutes. If I divide it over 60 once more, that gives me 55 hours. If I divide that 55 hours stuff over 24, that gives me somewhat around like this whole thing gives me somewhat like 55 hours, which is more than 2 days. Okay, question number 1. Are we okay that like, did I mess up something over here, or like, is it the correct derivation? That 55 hours is the amount of time required for computer A. And please like verify it by the time as you verify it. So I'm moving to the next one. So next one is that it's 10 million instructions per second. So as you said that 1 million is 10 to the power 6. So 10 million is 10 to the power 7 instructions. So now if you compare the speeds of both computers, so computer A is 1,000 times or 100 times faster than computer B, right? So computer B is 100 times slower than computer A. So which means that computer A is more efficient, and that efficient computer actually spent something more than 2 days to sort that large pool of numbers. So if you look over here on now the number of instructions, we need to decode number of instructions over here. So that is 50 multiplied by n. And n in this case is 10 raised power 7. And so if we, just to keep our calculations little simple, if I take log base 10 of n, so that means that I'm talking about this power, right? So log base 10 of 10 raised power 7 is 7. So this will give me 350 times, or maybe 35 times 10 raised power 8. So these many instructions are there for computer B to execute. So these are the number of instructions. And in order to find the time which is required to sort all those things in computer B, so that time looks somewhat like this. So this 30 number of instructions, 35 multiplied by 10 to the power 8 multiplied by 10 to the power minus 7 and this gives us 350 seconds. So if I convert them into equivalent minutes, so 350 divided by 60 is 5.8 minutes. So this gives us, I can round it to approximately that, approximately this is equal to 6 minutes. Okay, now over here you should take some time to understand what are we trying to do and why are we trying to do this thing. So if you like now look at computer A, that is sorting some numbers using a program. We are calling that program instruction sort, and number of instructions to execute in that program are larger than the second option. So, but that like 100 times faster computer is taking 55 hours to get that task done. The relatively slower computer, which is actually much slower, is taking only 6 minutes to get the same thing done on an input of the same size. So two things are different. One is speed. Speeds are like very different from each other. One computer is 100 times faster than the other. And another very important thing over here is that well, now that could be a question to you, that what do you think, like what is happening around? The times are different. One is 6 minutes versus 55 hours. So obviously 66 minutes is more attractive because things are getting done quickly, but on a relatively much slower computer. So the kind of thing which is making difference over here is who? Who is making the difference over here? Yeah, go ahead, Ayat. You wanted to say something?
I think the different is because the different of the algorithm that used to compute the number of instructions to execute.
Yeah, correct. So
In computer A, it's 2n power 2. That's in general, the algorithm is different. So this is why
excellent.
computer B better than A.
Very good, very good. Yeah, completely correct. And who is responsible for writing the algorithm? Who is responsible to write an algorithm on either of those machines?
The designer of
Yeah,
the
designer, that's
computer.
we, right? And now
Yes.
if we go for a bad decision, if we go for a poor, inefficient algorithm, then that's going to make a huge difference in terms of time, right? For the same task. So our hardware is not helping over.
Right.
So one thing which we need to convince ourselves that hardware is not that important as the algorithm's efficiency. Even for a like, so 100 times faster computer, if your design of the algorithm is not efficient enough, you might be messing up with time. Just your algorithm might be performing in a very poor way. So we need to be like quite curious and careful while making this decision of time. Any other question related to this derivation from any of you? Are all of us like okay with this thing? So the objective over here was to introduce you to this thing that uh, that's what we call algorithms efficiency, and that's what we call large scale input. So if input is really large scale, then like things matter, right? We need to be very careful. So if you look at the previous slide where I used that term of this large scale problems, so large scale for small scale problems, good and bad algorithms might not be very different because we have sophisticated hardware. So we have fast processors. They can like do almost okay for small scale data. But if the data is large scale, then your algorithms are like going to make a big difference irrespective of the quality of the hardware. So and that's the kind of thing which we are going to study in this course. We'll be focusing a lot on efficiency. We'll be focusing a lot on the performance of the algorithm, and that's what we call in this course we'll be calling this thing complexity. So complexity is something which will matter, right? So we will define complexity in a formal way. So if you've been given a set of numbers stored in one-dimensional array, find one of the peaks. That's what we already talked about. How would your algorithm change in its working as well as performance if you are supposed to compute the highest peak? So the kind of stuff which we're doing so far was to find a peak. Now, if we change the algorithm, if we change the problem, that we are interested in the highest peak, so try to figure out that how your logic will change. So this is somewhat like finding that the maximum number in the whole sequence, right? So that means that we need to change our if statement, we need to change the logic and then we move forward. Or another version of the same problem is that your numbers are now stored in a two-dimensional array, and our task is to find one of the peaks. So in a 2D setting, peak should be greater than all four neighbors. So if you look at this visualization, so these color codes represent different peaks. So if you look over here on this black point, on this black star where this core part is red, so around that red, that is we're calling it peak because things around that are smaller than that. So we look at left, we look at right, look at top and bottom, we look on all four sides. If all of them are smaller, we call it a peak. So I would strongly suggest that also try to practice this kind of problem using 2D arrays, populate some random data, and try to find a peak using a program. Okay. So this is another like homework kind of exercise. What is this? And we should be able to answer this kind of question if we are okay with the kind of discussion which we've done so far. What is the smallest value of n? What is the smallest value of input such that algorithm whose running time is 100 times n square runs faster than algorithm whose running time is 2 raised power n? So if you recall a little bit of math, 100 n square is a polynomial, right? 2 raised power n is an exponential. Exponentials are like fast growing functions. So what will be the smallest value of n where this exponential will give us better results? So that kind of exercise actually helps us to figure out that for what kind of small input size or small n, these complexities don't matter much. So the kind of thing which I want you to figure out is that if I put all those different n's in an Excel table, I compute 100 times n square. And if you look at the first row, when n is 1, 100 n square is 100. But the exponential function is giving me 2 answer. So in the next row, it's 400 versus 4, and it's 900 versus 8. So still the exponential is small. But after a while, if you keep on scrolling down, somewhere around 15, the things are switching. Or if you look at the same thing over here, so this blue line is the line representing 100 and square. So that is almost flat, which means that rate of growth is very slow. But if you look at the orange line, after some initial n, it grows at a very fast pace. And then things start making a huge difference if n is large. So the purpose of showing you this visualization is that for small n, this whole discussion of complexity, this whole discussion of execution time does not matter much, but it matters a lot if n increases. And that's the kind of thing which we have also seen in our that computer A and computer B example. So just to get familiar with the basic mathematical functions like logarithmic, square root, log, and those things, I would strongly suggest to fill this table on your own, that for what kind of n size, if algorithm is taking log n, so for what kind of value of n, things will be getting done with 1 second, 1 minute, 1 hour, or 1 century kind of thing. Try to fill it after the class for your own practice and for remaining days. Okay. Now we are getting into a more formal notation when we call asymptotic notation. So asymptotic notation is a mathematical notation to characterize efficiency of an algorithm. So mathematical functions are used. The functions primarily represent a characteristic of algorithm. So in our case, we are more interested in the running in the running time. So what will be the amount of time required to run an algorithm? So we'll notate that time using a function, and we'll think about different situations in terms of worst case time, average case time, and best case time. And the kind of three notations which we need to familiarize ourselves with are look at three notations. One is called theta notation. So the other one is called big O notation. We use this capital O. The third one is called this omega notation. So let's try to decode all three of them. So if we understand this theta notation, rest of the two notations are going to be relatively simple. So if you look over here, so all these three curves are essentially representing the running time of some algorithm. So okay, so if you look at the x-axis, so x-axis over here is representing, this axis is representing input size. When we say input size, that means that we are talking about the number of elements in the input. And the other axis, y-axis, is primarily representing the time or computational time for a particular algorithm, for a particular operation or a particular program. So n is 0 over here. So when n is 0, which means we don't have any input, that means that you're not spending much time on that. For smaller inputs, which we saw there in the Excel table as well. So if our input size is smaller than a threshold, that threshold is being notated as n naught. So if that is smaller than that thing, then that relationship is weird. Things like keep on jumbling up and down. But if you look at things after this dotted line, if you look at this part of the function plot, now things are now making a relationship. And that relationship is that there are three curves. So one curve is the one which is labeled as C1GN. We yet have to figure out what is C1 and GN. So that means that this is essentially the kind of thing whom we call lower bound. So this curve is binding the execution time from the lower side. So we call it lower bound. And a similar kind of thing is here on the top, that this curve is representing upper bound. And now the question is that what we are looking inside these two bounds. And so what does it suggest? It suggests that if execution time of our function is bound within these bounds, so it does not exceed these two lines. If our execution time stays within this thing, we can notate it as f of n. So f of n is something in between. And we notate it as theta of g of n. So theta of g, what is g of n? G of n is a function here in the upper bound. G of n is a function here in the lower bound. Both of the upper bound and lower bound are having a coefficient, which is a constant coefficient. One constant is notated as C1, other one is being notated as G1. So mathematically, what we do is that we say that this f of n is equal to theta of g of n. For what? How does this work? Why we are writing it as theta of g of n? Because you plot the plot which we saw there. This is f of n is somewhere in between two things. Those two things are being defined like this, that they are C2 g of n. So g of n is a generic function which is posing a bound on f of n function from both sides, from lower side and from the upper side.
G1, GN.
Yeah, go ahead.
GN.
Sorry, I didn't get.
I was continuing with you. I said that it's C1, GN, the lower bound.
Yeah, C1GN is the lower bound, right? Yeah. So if this pink relationship holds, then we say, because f of n is now bound within C1GN and C2GN, where C1 and C2 are the constants, we say that f of n can be notated as theta of g of n. Okay. Anything which does not make much sense till this moment? If it's okay, we can get back to this one if you would have a question, but let me move to the next notation, and that says that how do we define big O notation? So big O is the kind of notation which only poses the upper bound. It does not pose the lower bound, which makes our life little easier, right? So there's only one constant, which is CGN. So we represent things as the upper bound, and we don't worry much about the lower bound. So in this course, we'll be most of the time talking about big O. We'll be less talking about theta and omega. And so this big O is essentially covering one part of theta. And the last notation, which is omega notation, is essentially covering the lower bound and like overlooks the upper bound. So this like big O notation primarily is somewhat like the amount of time, the exact amount of time f of n can be notated as big O of g of n if there's a constant multiplied with g of n and we stay within that range. So if we impose that upper bound, if our running time stays within CGN, we go with that thing. Okay. Any questions so far? So for big O, we are only placing the upper bound. For omega, we are placing the lower bound. Why we are interested in this big O thing? So There is a huge variety. If big O has a small function, then rate of growth is small if n is very large. So if you look at on this colored graph, on x-axis we have size of the data, size of input. On y-axis we have the function which is representing time. So if we have like easy function like log n or n, so the rate of growth is slow. But for exponential functions and for bad functions, they grow like very fast. So we need to be very careful as far as the complexity is concerned. One of our major tasks would be to optimize the complexity of the algorithms in this course. So an algorithm is characterized by different things. One is correctness. It must be correct. That is the task number one. Task number two is its efficiency. It should be taking as small amount of time as possible. And then how to express that, how to write an algorithm. And building blocks means the small pieces which help us to constitute that bigger recipe. So one take-home task is that how can you guarantee that your algorithm is correct without running it on a machine? So this is not an easy task. Like little side question, have you ever taken discrete math course? The course related to formal mathematics, or you call it discrete math. The kind of stuff you study is like proof techniques, induction, or those kind of things. Yes or no? Have you taken that kind of course before?
Can you repeat the question?
Have you taken a discrete math course? Yeah, discrete mathematics. Okay, you've taken discrete math course. So and I assume that rest of the people would have also done. So like when we say that you are not allowed to run your program on the machine and just check it without running it, that means that uh, you need to come up with a proof. And this is an optional take-home task because some people are saying that they have not taken discrete math course. That's perfectly fine. You can just skip that task. So over here, I'm expecting you to think of some strategy of verifying whether that algorithm will be correct or not, right? So, but like that's not the core component of this course. We can skip that part. For those who have taken discrete math course, a quick comment is that you can think of using somewhat like induction or basic inductive principle, that how we can do this thing without running it on machine. Okay, again, pardon me for C++ syntax because this example is C++ and but should be fine. It has very closely related syntax to that of Java. From the coming class, I'll switch to Java. So this is a small function method whose name is find average. It takes an array of type double, real numbers as the parameter. It takes an integer as size, and then it runs a loop and returns something as float. So our task is to find its complexity. We are interested in finding out exact number of steps required to run this to run this code. So if you like now let's go line by line. So if you look at this line, double sum being assigned 0, so this takes one step. That's written in the comments. Count, again one line, takes one step. So how many times the loop is running? How many times this while condition is being checked? So if size is n, we are notating input size as n, and that small n variable will be used a lot in this course. And whenever we use this small n in this course, that means that we're talking about input size. So if count is less than size, that means that count is starting from 0. So 0 is less than size, then 1 is less than size, 2 is less than size. So we'll check it n times, and n times this loop will be repeated. But then there will be an n plus 1th time, an extra step, which will make the condition false. So this while condition is going to be checked n plus 1 times. But the number of steps which have been written inside the loop are going to be checked n times when the condition is true. So if you look at if condition, this if condition is being checked once. And in this return statement, we are writing 2 because there are 2 steps over here. One is that we are computing this thing, sum over size, plus we are also returning it to the place where this method or function was called from. So we're calling it 2. We can call it 1. That's not going to make a huge difference. And then we have a statement at the end, which is 1. Now, if you sum up all these numbers, they are 1 plus 1, 3. So n plus n plus n. So 3n plus 4, 6, and 7. So it looks like 3n plus 7 kind of thing, right? Is that correct calculation? So 1, I'm just counting the constants. This is 1, 2,
Right.
3, 4, 6, and 7. And then there are 3n. So total number of steps are 3n plus 7. So what is 3n plus 7? So this is exactly, these are the exact number of steps required to run this algorithm, right? So what we do over here is that we use some basic principles to notate this thing in terms of big O. So the total number of steps are 3n plus 7. So now our task is to find computational complexity. So whenever we'll refer to this thing, computational complexity, so in this course, computational complexity will mean that we are now talking about big O. And then there are some basic principles. So like if I use that capital O big O notation over here, so I write this exact number of steps inside it. So this is 3n plus 7. Now, the basic principles are that in order to, because this computational complexity is an approximation, is bound within that constant kind of thing. So, and while writing that big O, you might have seen that thing that if it is CG1, CGN, so we don't really look at C, we ignore it, and we write it as big O of G of N. So what we do is that all those constants which are being added or subtracted over here, or all those constants which are being multiplied over here, we skip them, we omit them. And this is equal to big O of n. So this function, big O of n, essentially represents the computational complexity. And if you look over here, so n is the representation of something which is a linear function. So if you look at exact number of steps, they are linear. 3n plus 7 is a linear function, right? So big O n is the computational complexity or notation for that particular function. Does that make some sense? Any question till this moment? Good. So let's move forward. So like these are the kind of principles which we have just applied over there. So if there is a polynomial which has multiple terms in it, we eliminate the lower order terms. What does that mean? That means that if your number of steps are turning out to be something like, for example, 2n square plus 7n plus 4, so we can conveniently eliminate the lower order terms. So over here, n is n raised power 0, is n raised power 1, so they are eliminated. So we are left with this thing. And over here, we apply that basic definition of big O. We ignore the constant, and n square is the big O of that whole expression. So that's what it means. Ignore coefficients. Big O simplifies the analysis of algorithm by focusing on the most dominating term. So this is an approximation to give us a very good clue that how good or bad is the algorithm. And it represents the complexity, represents the efficiency of that particular algorithm in a very efficient and simplistic terms. Okay, now let's have a look on something on an algorithm. So this algorithm is not written in a particular programming language. So this is a mathematical way of writing algorithms. We call it pseudocode. So this is the code which looks like code, but this is not executable code. right? So pseudocode is a mix of mathematical and programming notations. We just try to write our idea or logic in a straightforward way. So this is pseudocode of an algorithm. So this algorithm is called linear search algorithm, which means that we have been given an array A. We know size of the array. We also know key. Key is the kind of thing which we are interested in locating in the array. We scan the array from its first to last index. And because this is not written in a programming language, that's why we are writing over here 1. For Java and C++, usually we write here 0. And then within the array, we are comparing an index against key. If we find it, we return true. If we fail to find the key, we'll get out of the loop and we'll return false. So let me try to remove this labeling, which I've put over there. Take a look at the algorithm. Are we okay with the purpose of the algorithm? So there's an array which is being scanned, starting from its first index to the last index. And we compare every element against something which we are looking for that is being termed as key. If we succeed to find it, we return true. Otherwise, it returns false. So our task over here is to estimate the complexity. So in order to estimate the complexity, the first thing which we do is that we estimate the number of steps number of steps which are required over here. So for the first line, the kind of stuff which we did for our previous code snippet. So the number of times this for condition is being checked, this is going to be n+1. So for n times it's going to be true, but in order to stop it, then there will be n+1th time when it will become false. And then this if condition is because it's inside inside the loop, so this will run n times. Okay. Any guess how many times or maximum number of times this line will execute? Any guess? How many times return true will be executed?
N times?
One.
N times?
One time.
Yeah.
Why one time?
One time because if it's true, well,
Very good, right? So because if as we reach to the statement, so we know return statement stops the algorithm. It stops the program.
Yeah.
So as we reach here, there's no way that it will be repeated once more. So at max, it will be executed once. And this last line will be executed once at max. So if we sum up all these individual expressions, so this gives us 2n plus 3 is that total number of, so this expression is representing the total number of steps required to run algorithm number 1. And what we do over here is that we use those basic principles. We drop the low order terms, we drop the coefficient, and this whole thing takes us to something which is big O of n. Okay. And then what we do is that, so then we have another algorithm, so which is called binary search algorithm. So what I can do is that like it might become like a little bit of overdose if we start deriving this right away. So I can splash the screens, but like the promise is that from our next sessions, we can start from this binary search algorithms, binary search algorithm, and this might be a little more involving. I would strongly suggest you as a homework that try to understand this algorithm, code it using Java. And the reason I'm asking you to code it in Java is that you might be able to like see things over here that this function is calling itself over here, which means that we are talking about recursion. Right, so we should be just comfortable with its implementation, that how this whole thing is working. And then from our next discussion, I'll try to we'll start from this point, and then we'll move forward in our discussions. But like I can splash through the screen just to give you an idea that what will be coming afterwards. So this is kind of basic definition of BICO. And then there are some practice problems. So I would strongly suggest that do these problems, that what are when we say 2n plus 100, is it really big O n? So big O n is the like whole like range of possibilities. So is it true or false? So you have to just answer these things as true or false. And as binary search algorithm is the algorithm which we yet have to figure out. So if you succeed to do it on your own, that's fine. Otherwise, we'll be solving these questions again in our coming time. So if you look at this task, this is an algorithm. We call it mystery algorithm because we don't know what is happening around. So try to decode on your own. What does this algorithm do? This syntax is pretty much similar to Java, though I wrote it in C++, but this is like very closely related to Java. Just look at this function, try to figure out what does this do, compute the exact number of steps, estimate the time complexity, and then this is another code. So this is different than the previous one. Try to figure out again what is happening over here. What are the exact number of steps? What is the time complexity? And that's it for today. So the kind of stuff which I'll be showing you on these slides, this has been like borrowed from a bulk of stuff. So I've put up over here some references just to keep things legal. But yeah. So in the next few minutes, I should be uploading these things on Raza Moodle, so you should be able to access that. If you have not joined the WhatsApp group, I would strongly suggest join the WhatsApp group. And as all of you have suggested, we are moving to Java, so you don't need to worry about C++, right? So I'll change things accordingly. Thank you very much. If you have any questions, please feel free to let me know.